All right, so if we rewind the tape and go back to where we were Monday, we ended Monday talking about this concept of collision theory. And we said that we're going to tie everything back to collision theory by the end of this to talk about why reactions can be sped up or slowed down by different kinds of processes. And so we talked about the idea that in order for a reaction to occur, it had to occur with two different things. First of all, we had to have a collision between the reactant particles. And that collision not only needed to happen, but it also needed to happen with proper orientation. That means the molecules had to be pointed to each other the correct way, and it had to have enough energy to break the bonds that were going to be broken. And we also ended with the concept that overall, only a small fraction of collisions actually can do this. So there are some other ways we can represent collision theory that kind of fit into this mold. First of all, we can talk about energy from the idea of an energy diagram. That is, there are two primary types of reactions. We've talked about them in the past. There's the endothermic reaction and the exothermic reaction. And notice that the difference between them has everything to do with the energy of my reactants versus the energy of my products. When my products are of a higher energy, then we call that an endothermic reaction. When my products are of a lower energy, we call that an exothermic reaction. Now, of these two reactions, which one of these reactions would we expect to be easier to do from an energetic standpoint? The endothermic, yes. Well, the endothermic is actually going to be more difficult because we're going to have to continue to supply it with energy to raise up those reactants to the proper energy of the products. Whereas with the exothermic reaction, since the energy is going to fall as the reaction proceeds, the reactants are losing energy and they're just giving it away. So from the standpoint of us on the outside, this reaction requires very little in the way of outside interference. But it does require some interference. All reactions require some amount of interference. We call that interference activation energy. Activation energy is the energy that is required to break the bonds in the reactants in order to help those reactants reform new bonds to make products. We can think of energy as a barrier. And so any reaction is going to have an energy barrier that needs to be overcome. And we call that energy barrier the activation energy. When our activation energies are large, we tend to have slow reactions. Again, think about the diagram that we just showed you. The more energy that is required to be inputted, the more energy we have to continue to put into the reaction, the more difficult the reaction is going to be to run. From a collision theory standpoint, it's that sufficient energy aspect. If I have a large activation energy, It's going to require much more energy to get to that sufficient energy of collision to get the reaction to occur. By contrast, if I have a small activation energy, those reactions tend to be fast. And the reason they tend to be fast is because they require less energy overall, which means that more of the reactants are going to have sufficient energy overall. So activation energy plays a significant role in the ability of a reaction to be effective or ineffective, to be fast or slow. If I have a large activation energy, I'm going to have fewer effective collisions, which means I'm going to have a slower reaction overall. If I have a low activation energy, I'm going to have more effective collisions because it's not going to require as much energy to get an effective collision. Now let's put this into some of the contexts of some of those conditions that we identified on Monday. So surface area, concentration, both can be kind of explained away in the same manner. When I increase my concentration, when I increase my surface area, what is happening is I'm exposing more substance to react. And when I have more substance to react, there is a better chance I'm going to have more collisions. And by having more collisions, there's a better chance I will have more effective collisions as a result. So why does the steel wool react more quickly in this drawing compared to the iron nail? Well, by separating those strands from each other, I have more iron atoms that are exposed to the oxygen at one given time. And so long as I've got enough energy in there to meet the activation energy, I have more atoms that are capable of colliding, and therefore more atoms that are capable of having good collisions that would cause a chemical reaction. When I increase concentration, what happens is if my temperature remains the same, increasing the concentration is going to increase the total number of collisions. But since I have more molecules present, having more collisions means I'm also going to have more effective collisions just by sheer magnitude of number. So in this panel here on the left, I have 3 ozone molecules and 3 nitrogen monoxide molecules. In the end, one of them will react to give us nitrogen dioxide and oxygen. The other 2 will be left behind. in the panel here on the right, I have 6 ozones and 6 nitrogen monoxides. In the end, 2 of those collisions are effective, so I'll end up getting 2 NO2s and 2 O2s. The panel on the right, in terms of percent effectiveness, it's exactly the same. 1/3 of the collisions are effective. But by sheer number of collisions, I will end up getting more product in the right-hand panel than on the left. And so the reaction will proceed a little bit faster in that panel as a result. So that's the effect of concentration. Simply increasing the number of particles means I'm going to get more collisions. And just by simple statistics, if I get more collisions, I will also get more effective collisions and more reaction as a result. All right, any questions so far? All right, let's look at the other 2 factors then. What about temperature? With temperature has a direct impact in terms of the amount of energy that is present in the molecules themselves. When I increase the temperature, I'm also increasing the energy of all of those particles, which means that with an increase of energy, there is a likelihood that I'm going to meet the activation energy required for reaction more often. So this has a twofold effect. First of all, because the molecules are moving faster, they are more likely to collide with each other. As we saw in the previous slide, simply increasing the number of collisions will result in a greater extent of the chemical reaction. But in addition to that, increasing the temperature, in addition to getting those molecules moving more quickly and colliding more often, when they collide, more of them will have the energy required to react. So if you look at the graph here, this line here represents the activation energy for the reaction. The blue graph represents the energy of collisions at a low temperature. And so we can see that the majority of the reaction, the majority of the collisions do not have enough energy to actually force a reaction. But there are some here that do. And so the reaction will proceed to some extent. But if I raise the temperature, notice that the majority of my molecules still don't meet the activation energy, but a significant portion of them do. And I get a larger proportion of those molecules that react with enough energy to cause a chemical reaction. And as I increase my temperature, I will see that this line creeps more and more and more onto the other side of activation energy. So the more I increase the temperature, the more energetic the collisions become, the more of those collisions are going to be ones that result in a chemical reaction. All right, let's look at the last factor, catalysts. Now with catalysts, what we get instead is a catalyst creates what we call an alternative pathway. And that alternative pathway results in a lower activation energy. So if we compare the red line, which is our uncatalyzed chemical reaction, with the blue line, which is our catalyzed chemical reaction, we can see that with a catalyst, even though the process is different, we end up getting a lower activation energy as a result, which means that at the same temperature, more and more of those reactions, more and more of those collisions are going to be effective. So I've lowered activation energy, and by lowering that activation energy, I've increased the number of effective collisions from an energy standpoint. And as a result, the reaction proceeds faster because I get more of those good collisions. Now, why does it take this alternative pathway? Well, the primary reason is going back to what a catalyst is. Remember, a catalyst is not a reactant or a product. It's going to interact with the reactants, but by the end of the process, we're going to get the catalyst back. And so that's why it has to take an alternative pathway. The pathway it has to take involves it reacting with the reactants to form intermediate products that eventually will become the actual products. And so since the reactant catalyst is not actually disappearing, we can effectively recycle them over and over and over again. And small amounts of a given catalyst can last long, long times overall. Probably one of the most common places where we see them are things like catalytic converters. In a catalytic converter, a small piece of platinum or palladium is lined onto the exhaust system, and all of that platinum or palladium does is it just gives a place for oxygen and carbon monoxide to rest. The oxygen and carbon monoxide sit on the catalyst of the catalytic converter, and the catalytic converter helps them to break apart into individual atoms, thereby giving us carbon dioxide instead of carbon monoxide. The enzymes in our body react in a similar manner to do kind of the same thing. The substrate, the reactants of the biological process enter into the enzyme works on them, causes them to interact with whatever it is that they need to interact with, and the net result is that we get the products that we seek at the end. A specific example of this would come in the form of the enzyme Sucrase, which works in the form of breaking down your sucrose. So table sugar, sucrose, is a disaccharide, consists of two different sugars, glucose and fructose. What happens is that sucrase is a large enzyme that has a pocket in it that kind of accommodates, see how this is bent in its structure slightly? That bent structure slides over into this bent part of the enzyme. And basically what the enzyme does is it strains on that, stresses on that bend to pop off the two rings, the glucose ring and the fructose ring, from each other. And once that happens in your body is able to process glucose and fructose much more rapidly, much more efficiently from an energy standpoint than it was able to with sucrose. So with many biological processes, we really get into shapes of molecules and active sites that are very specific. So sucrase really only works with sucrose because its bend, its structure, those pockets really only fit those two rings. And so if I put in a different sugar in its place, it wouldn't fit properly and the enzyme would reject it as a result. All right, we move now into section 3 here, where we talk about chemical equilibrium. Now, we've already alluded to chemical equilibrium in a couple of different ways in the past. Essentially, chemical equilibrium discusses a concept that, again, we've made mention of, but we haven't really defined explicitly. The idea of a reversible reaction. A reaction where the reactants turn into products, but the products also turn into reactants at the same time. Now, what's important about chemical equilibrium is understanding two things about it. First of all, there is no net change in concentration when a substance or a chemical reaction system is at equilibrium. There's no change. So that's the first thing that we have to understand. My reactant concentrations and my product concentrations are not going to show any signs of change when the system is at equilibrium. However, what's important about this is that even though we're seeing no net change in concentration, that does not mean that the reactions are stopped. Both processes are occurring at an equal rate to each other. That's why we don't see any change. But the forward reaction is still going. The reverse reaction is still going. Both reactions are occurring at the same time. They just happen to be occurring at the same rate. So to us on the outside, we see no net change. But inside, there are constant changes going on at the microscopic level. And so for that reason, chemical equilibrium is referred to as a dynamic equilibrium state, meaning that it is showing equilibrium, but the processes involved are still in motion. This is different from something like a static equilibrium. The static equilibrium, imagine that you have a seesaw. Now, when you and your brother or sister are on the seesaw, you go up and down according to each other's weight and the forces that you're exerting. But if you're in the middle and the seesaw is sitting perfectly still, this is an equilibrium state as well. You and your brother are not moving. yet neither is the seesaw. This is what is called a static equilibrium. Many things exist at static equilibrium, where there's no net change in position, there's also no motion at the same time. Chemical equilibrium systems are not static. They are dynamic. And the proof that we have of this dynamic state comes from a concept known as Le Chatelier's Principle. Le Chatelier's Principle tells us that if we are in a state of dynamic equilibrium and we introduce some kind of external stress to that system that knocks it out of equilibrium, it will reset to get back to equilibrium. What Le Chatelier's Principle allows us to do is it allows us to predict how the system will react, how the system will adapt to reestablish equilibrium overall. If our equilibrium were static, then Le Chatelier's Principle would not happen. If you're sitting on the teeter-totter with your brother and you're at a state of static equilibrium and the kid next door jumps on to the other side, you don't reestablish equilibrium from that state. You're stuck where you are. The side that had the heavier objects on it is tipped. You are up here in the air waiting for someone to let you come down. That's what happened if it was a static equilibrium, because there's no opposing force that's allowing this side to come back to where it was. But with a dynamic equilibrium, because both processes are occurring at the same time, if something happens to the one process, the other process can adapt by either slowing down or speeding up to adapt to that adaptation, to adapt to the stress that has been added. There are three primary ways that we can see an equilibrium system be disrupted. One of them is changing concentration. So if I add a product or remove a product, if I add more reactant or take a reactant away, that would disrupt the equilibrium. And the equilibrium would have to adapt to that situation. If I change the volume of the reaction container, that would have an impact as well. If one of my reactants or products was in the gas phase. If I'm dealing with a reaction in aqueous solution, changing the volume of the solution, changing the volume of the reaction container is not going to make any kind of impact. This second one only is for gas phase reactions. And then the last thing is the changing of the temperature. And changing of the temperature, we look specifically endothermic reactions and exothermic reactions are going to have different impacts on temperature change. All right, let's end today by doing this first type of disruption. So what is the impact on concentration? So let's take, for example, this equilibrium system that we have right here. In this reaction system, we've got iron 3 coming in the form of iron 3 nitrate and the thiocyanate ion coming in the form of potassium thiocyanate. When these two come together, they will form a complex ion known as ferric thiocyanate complex. This complex is well known for its blood red color. Now the question is, when we add more iron 3 nitrate or more potassium thiocyanate, what would happen to this equilibrium system? And the answer there is going to be that we're going to form more complex. Now, how do I know that we're going to form more complex? Well, this is where the Chateliers principle comes into play. When it comes to concentration changes, what Le Chatelier's principle states is that whatever change we see happen, we're going to see a shift to replace that stress. So if I add reactant, we're going to see reactions go to get rid of the extra reactant. If I see an increase in product, we're going to see a shift to get rid of the extra product. If I see a reactant or a product removed, the equilibrium is going to shift to replace what was removed. In simple terms, we refer to these shifts as shifting right if we're going to make more products, or shifting left if we're going to make more reactants. So a shift to the right indicates that the forward reaction is going to take over. We're going to get the forward reaction to occur more quickly for a while. And as a result, we're going to get more products made in the end. A shift to the left means that the reverse reaction will take over, and we'll get more reactants made as a result. So I go back to this problem here. What happens if I add more reactant? Well, Le Chatelier's principle tells me that adding more reactant is going to cause the shift to go away from the reactants. We're going to see a shift to the right, which means we're going to get more of this blood red complex. And that's what we see in panel C there. So from a concentration standpoint, when we change the concentration of one of our reacting species, whether it's in the reactants or the products, Le Chatelier's principle basically says that the opposite effect is going to happen. If I increase the concentration, we're going to shift to get rid of that concentration. If I decrease the concentration, we're going to shift to replace it. And that's where we'll stop for today. Friday's going to be all the Chatelier principle. We're going to talk about the other two parameters. We're going to talk a little bit more about concentration, but that will close out chapter 12 for us. That'll be the last bit out of it. Have a good afternoon.